Hi everyone and welcome. In today's video, we are going to take a look at some properties of the definite integral. So this is going to be building off of the previous video in which we introduced the definite integral. The definite integral, as we saw, is the limit of the Riemann sum. And if your function is continuous, then the limit of the Riemann sum will approach a unique single value, no matter how you partition the interval or which sample point you pick within the interval to define as the height of the rectangles. And so as a result, the left endpoint, the right endpoint, the midpoint approximations will all approach special unique number, and the definite integral denotes that special number. So now let's take a look at what are some properties of the definite integral. The first property of the definite integral deals with reversing the limits of integration. So this property says that if you were to reverse the limits of integration, then you have to pick up a minus sign. The next property is saying that if you were to integrate over the interval from a to a, then the value of the definite integral is just 0. And that makes intuitive sense because you're basically integrating over an interval that has no length. And so there's no area under the function on that interval. The next property says that if you integrate a constant function, f of x equals c, then you get c times the length of the interval. And to give you intuition about why this is true, you can think of the constant function as a horizontal line, and we're integrating over the closed interval from a to b. And so we're basically finding the signed area of this region between the x-axis and the graph. And this is just the area of a rectangle. And the area of a rectangle is width times height. The width is going to be b minus a, that's this quantity, and the height is going to be c. So that's where the c is coming from. The next two properties are the linearity properties of the integral. It basically says that the integral behaves how you would expect it to with sums and constant multiples. So if you take the integral of a sum of two functions or a difference of two functions, well then you can just take the integral of the first function plus minus the integral of the second function. And if you want to think of this in terms of areas, let's suppose that we have our first function f in orange and our second function g in blue, and then f plus g is just adding the outputs number by number to get this f plus g function. And so the definite integral represents the signed area. In this case, we're just going to be adding up the area under g and the area under f, and that will represent the area under f plus g. The next rule says that if you're integrating a constant times a function, then you can just take that constant out of the integral, find the value of the definite integral, and then scale that up by the constant. The next property is the additivity of adjacent intervals. So let's say you have the integral from a to c plus the integral from c to b. So a to c and c to b are your adjacent intervals. Then you can write this as a single definite integral from a to b of f of x dx. In terms of a diagram, here's what's going on. The first definite integral represents the signed area under the curve from a to c. The second definite integral represents the signed area under the curve from c to b. And so we can just simply take the signed area from a all the way to b, and that would be represented by this definite integral. Another important thing to note is that this also works when c is not in between a and b. So c could be somewhere over here or somewhere over here, and this would still work. So you would maybe integrate from a to c and then from c to b, and then these will sort of cancel out and you'll just get this integral. So the proof of this property in general is quite tricky, but luckily in our course we're just focusing more on computation and the main ideas behind integral calculus. For proofs, you can take a look at our course on real analysis. Great, now let's take a look at our first example on how to apply some of these properties. So let's say we want to compute the definite integral from 0 to 3 of minus 3x minus 7 dx. Now using the linearity properties of the integral, we can distribute this integral sign over the difference, and we can also pull out constants out of it. And that will lead us to this step over here. You can see the minus 3 has been factored out. And here I left the 7. Now the goal is to evaluate these two definite integrals. And remember, definite integral represents the signed area under these functions. And these are very simple functions, and so we can just compute the areas under these functions using simple geometry. For this first definite integral, we have the function f of x equals x, and we're integrating from 0 to 3. So this region is a triangle. The area of a triangle is 1/2 base times height. The base is 3, the height is 3, then we plug it into the formula, and the area of this triangle is 9/2. And in terms of signed area, since this region lies above the x-axis, it's going to be positive 9/2. So that's why I put positive 9/2 here. For this integral, as we discussed above, you're integrating a constant. So it's basically the signed area of a rectangle. So you take the height, which is given by 7, and you multiply by 3 minus 0, which is the width of that rectangle, and you get this area. I've also shown a picture over here. Now we just go ahead and multiply this in your calculator, and you get negative 69 over 2 as the final answer to this definite integral. For this next problem, we're given the value of the definite integral from 0 to 10 of f of x dx to be 17. We're given the value of the definite integral from 0 to 8 f of x dx as 12. And they are asking us to find the value of the integral from 8 to 10 of f of x dx. So let's make a quick diagram to reason about these integrals. Let's say that this is y equals f of x, and then it looks like we have some unique numbers here. And then the numbers that we're interested in here are 0, 10, and 8 is what it looks like. So here's 0, here's 8, here's 10. Now we want to find the value of the integral from 8 to 10. So we want to find this signed area. And they have given us the entire signed area from 0 to 10 and the entire signed area from 0 to 8. So what if we just took the entire area from 0 to 10 and subtract the area from 0 to 8? Then that will leave us with the portion that we want. And so that's what we've written over here. The integral from 8 to 10 of f of x dx is simply the integral from 0 to 10 f of x dx minus the integral from 0 to 8 f of x dx. So 17 minus 12 gives us 5. Or if you think in terms of the property says that if you integrate from 0 to 8 and then from 8 to 10, it should give you the entire signed area from 0 to 10. And this is the integral that we're interested in. So just go ahead and isolate for it just by rearranging and bringing this term over here, and you'll get back to this expression here. So yeah, you can either try applying the property or just reason about it geometrically. Either way, you will end up with an answer of 5. Next up, we have a few more properties of the definite integral, and these are called the comparison properties. The first property says that if f of x is non-negative, that is that it lies above the x-axis, and you're integrating on the closed interval from a to b, then the value of the definite integral is going to be non-negative. So in this case, it just represents the area under the graph. The second property says that suppose f of x is greater than or equal to g of x on some closed interval from a to b, then the signed area of f is going to be greater than or equal to the signed area under g, right? Because if your two functions are non-negative, then the area under the smaller function is going to be less than or equal to the area below the upper function. And you might be thinking, is that true for even negative functions? And yeah, because if g of x is smaller, then it's going to be even more negative than f. As a result, its signed area is going to be even more negative than the signed area of f. So yeah, it will still work out. And the last property states that if your function f of x is bounded between two constants, so there exists this lowercase m and this uppercase m, so that f of x is at least this big and at most this big on some closed interval ab, then we can apply the property that we just talked about to integrate all sides of this inequality, and we get that their integrals satisfy this inequality. But then we know what the integral of a constant is. It's just the constant times the width of the interval. Same thing over here, it's going to be the constant times the width of the interval. And so this is great to get a rough estimate for the value of a definite integral. Previously, in order to approximate definite integrals, we have to use Riemann sums. But now if you want to get a very quick estimate, you can also use this approximation. And visually what this is saying is, let's say you have your function y equals f of x, and let's suppose that the lowest value it takes on is right over here. This is m, right? So the function is at least m. And then let's suppose that the highest value the function takes on is capital M. So the function is at most capital M. Then the definite integral represents this area, right? It represents all of this area. And what we're seeing is that area is at least this big, the area of this rectangle, and at most this big, the area of that big rectangle. That's precisely what this property is saying. This represents the signed area of the small rectangle. This represents the signed area of the large rectangle. And so the true value of the definite integral lies somewhere in between those two rectangles. Now let's do some examples applying these properties. So the first example says to prove that the definite integral from 1 to 4 of 1 over x squared dx is less than or equal to the definite integral from 1 to 4 of 1 over x dx. And so this sort of resembles the second property, where if we can show that one function is bigger than the other one, then their integrals also satisfy the same inequality. So that motivates why we want to possibly show this function is greater than or equal to this function. So to get started, we know that we're integrating on the closed interval from 1 to 4. That is, x is at least 1. Well, if x is at least 1, then I can go ahead and multiply both sides of the inequality by x, since it's non-negative and don't have to worry about flipping the sign. So I get x squared is greater than or equal to x. Now we can take the reciprocal on both sides, but when we do that, the sign of the inequality flips. Because if this number is bigger than this number, then when you flip it, the reciprocal will become smaller. You're doing 1 divided by a much bigger denominator than what you're doing over here. So this will be a larger fraction than this one. And so this means that the function 1 over x squared is less than or equal to the function 1 over x on this domain. In fact, it's going to be true for x greater than or equal to 1, but we just need it on this closed domain. And so therefore it follows by one of the properties that I talked about above, that the definite integral will also satisfy the same inequalities. That is, the definite integral of 1 over x squared is going to be less than or equal to the definite integral of 1 over x on this interval. This is going to have a smaller signed area than this signed area. And let's take a look at one more example where we practice using the last property to get rough estimates for the value of a definite integral. So here they're asking us to estimate the value of this definite integral from 1/2 to 2 of the function 1 over x dx. So to apply the third property, you have to find these lower and upper bounds. And in this case, it's going to be pretty easy because the reciprocal function or the hyperbola is a strictly decreasing function on this domain. As a result, the highest value that this function will attain on that interval is going to be at the left endpoint. And so therefore we write that the absolute maximum, which is denoted by capital M, is going to be the function evaluated at the left endpoint, which in this case is 2, right? The reciprocal of 1/2 is just 2. And similarly, the smallest possible value attained by this function on that closed interval has to be at the right endpoint because it's a decreasing function, right? It's a strictly decreasing function. So at the right endpoint, it's going to be the smallest possible value it can attain. So lowercase m is defined to be f of 2, which is equal to 1/2. In case you're wondering how this function looks like, the hyperbola or the reciprocal sort of looks like this. And as you can see, it's a decreasing function. The highest value it will attain is at the left endpoint. That motivates this. And the lowest value it will achieve is at the right endpoint. And that's what motivated this idea. And so the inequality that we get is the function is at least 1/2 and at most 2 on this closed domain. And now we're just going to apply integrals throughout this inequality. And the idea will be to show that the area underneath the reciprocal function is at least as big as the area of this rectangle and at most as big as the area of this big rectangle. So as you can see, if the functions satisfy this inequality, then their signed areas also satisfy this property by the comparison properties. And then these are the integral of constants. The integral of constant is the constant times the width of the interval. Constant times the width of the interval. And so therefore, the value of this definite integral is at least 3/4 and at most 3. And there we go. We have gotten a rough estimate for the value of this definite integral. And so that brings us to the end of today's video, in which we covered some nice properties of the definite integral. In the next video, we're going to start taking a look at something called indefinite integrals. And so I hope to see you then. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.